All right, today we're going to explore why when you have an object and you heat it up, it can give off different colors of light. And what do those different colors of light really mean about the object? Further, how can these objects that are heated up on Earth end up telling us about the mysteries going on inside of stars far, far away? And then we're going to talk even more about how these objects, looking at heated up objects, ended up upending the entirety of physics and was really the crack in the foundation of classical understanding of light. It's going to change everything we think about waves and the way light is a wave. So let's get started. Here we have an object that's being heated up. And you notice that there's different colors happening here. We have red light coming off down here, and then we get yellow, and then as we get up further, we get into orange, we have orange, and then we get into a yellow. Why is that happening? Here we have on the right, we have a piece of iron being heated up by a blowtorch. And down in the bottom, you see red. Why is that? Because that part actually has the lowest temperature. In other words, you are shoving energy into this thing. It is absorbing some of it. Some of it's coming back off reflective, but it's absorbing some of it. And then once it's absorbed, it's going to give off that energy again. Now, because it's absorbed it and a little bit's been lost, it's going to come off as a little bit slower. Okay? When we look at that light, it can give us an indication of how hot the particular object is. So right down here on the bottom, let me get my pointer here. Down here, it is quite red, okay? So that means that in terms of energy, if you look at the little color spectrum here, remember red is low frequency, so low energy, and indigo is high frequency, high energy. So this is only giving off a little bit of energy, so it's going to appear red. If you get up hotter, when you go a little bit higher here into this area, we start giving off more energy. So we're still giving off some wavelengths that are lower energy, but we're also now giving off higher frequency. So we're getting into higher energy. So you start to get this, like, your brain interprets that as like a yellowish orange. Now, what about up here? If we go all the way up to the top, we start to get this like bright kind of white light. What's causing that? Well, that means that you've hit a place where you're kind of doing most of the spectrum. And so you're giving off red light, yellow light, green light, blue light. And what does your brain interpret that as? Your brain interprets all those frequencies coming in as white light. So white is actually the hottest. I talked about how an object, when it's absorbing energy, in comes the energy. Some of it is going to come back off. Some of it's going to go inside, be absorbed, and then it's going to re-emit it off like this. So when we talk about black body radiation, what we are talking about is an idealized system, so sort of like a frictionless table or a room without air resistance. It's one of those things that physicists like to talk and think about. It doesn't actually exist, but we can kind of approximate it. This would be like you send energy in, it gets perfectly absorbed, none of it comes back off, so you don't have to worry about it, and you can watch what's coming out. So we found objects that were pretty similar, and we're going to talk about that. Ones that do not reflect basically anything are actually kind of the opposite of what you think a black body would be. A really good example of black bodies in the universe are actually stars. How can stars be black bodies? Well, the original idea of a black body seems like it would be black, and that kind of makes sense. A black body would be something where you send in energy, it absorbs it, and it absorbs all of it. It doesn't let anything reflect back off. It will then re-emit the light. Okay? And that makes sense that the object would look black because you're not getting any reflection off of it. So how in the world would a star count toward this? Well, let's look at a star real quick. When you look at a star, it looks like it would be the complete opposite opposites of a black body because, it's glowing. But remember that if you take a black body and you heat it up, it does still glow. It does still emit light or energy coming off. And that's exactly what a star is. A star is just something that's been heated up due to the nuclear reaction going on inside of it, and it is glowing a color that reflects the temperature that's sort of happening inside of it. So when you go outside and you look up at the stars, it looks like they're all white. But if you're out somewhere where it's really dark and you look up, you'll actually see that the stars are all different colors. There's red, there's yellow, and there's blue in particular. It's actually by looking at these colors of these black bodies, these stars that are not reflecting light but are putting off light, that you can actually tell the temperature of stars, even stars that are really, really far away. Later on in this class, in our next section, we're actually going to look at how you can just look at the light of a star and you can actually tell what sort of stuff it's burning. But we'll get to that later. So how did these black bodies end up causing basically a riot inside of science? Well, first of all, remember that when you heat a black body up, it would give off different kinds of radiation or, light. So let's talk about what that would look like. At this point in science, scientists believe that light was a wave, and they had a lot of evidence, and none of that evidence that we're going to look at is actually going to prove to be is not going to prove true. One of the pieces of evidence that you're probably most familiar with was the double slit experiment, which said if you sent light through the double slit, you would end up getting an interference pattern on the wall. So that shows, light is a wave. Everybody feels really comfortable with that, and everybody is really happy. But then you look at these black bodies, and I'm not going to get too into it because the math is a little bit beyond this class. But they predicted that if you heated up a black body to a certain temperature, you would expect to get a lot or a ton of intensity of high energy, low wavelength waves. So we get a lot of light like this. And you would get less light of lower frequencies. So you would get a little bit less of a lower frequency range, and you would get even less of the longer guys. I should make that look less. So you get even less of the low frequency wave, and you get very, very, very little of this guy. I'm not trying to show the amplitude, I'm just trying to show the amounts that you would get off. So they were predicting a lot of intensity for the high guy, and less and less and less the lower energy you want. So what really happened was when they heated up these black bodies, they ended up seeing something kind of unpredictable. They actually saw less of higher frequency waves, and then they would see even more of something of a lower frequency, and then kind of a middle amount of the next guy, and then even less of this guy. So it would kind of cluster around one color, and that freaked them out. You can just picture when you look at this, scientists swearing, just like a whole stream of swears coming out of their face, because this told them it didn't match their math of what waves would do. And that was a huge problem, because how could one experiment say light's a wave and another say it's not? Just to get a sense of how truly devastating this was and how off scientists really felt they were and were, this is a graph of what they expected versus what they actually found. So here we have what they expected, which is as your wavelength gets shorter, in other words, as your frequency increases, you should get greater and greater intensity coming off. So the frequencies of light that were very high you would have seen the most of, and you would have seen very little of the type of light that is longer wavelength. Now I keep using light, which is terrible. What I'm talking about is actually like the visible spectrum, or is the spectrum of light that includes invisible portions such as infrared and UV, just so you're aware. Anyway, so this is what they thought would happen. And then these other colors are what nature actually did. So if you took an object and you heated it to 300 Kelvin, you would see at first it starts to sort of follow your path. Yes, okay, great. As we go, we're seeing more and more and more intense light. But then it would sort of reach this point where you'd get to a certain wavelength or a certain frequency, and it would peak out. And then after that, you would actually see less and less high frequency light. It was as though it kind of like reached a peak and then it was dropping off. I mean, that's exactly what it was. And then they tried at a different temperature. So they took the same object and they heated it to 4,000. And they're like, well, okay, going good. Okay, we're getting more and more intensity of light at higher frequencies. And then all of a sudden it would just drop off. And there, okay, there's the swearing. That's the swearing part right there. Same thing with even higher temperature. In fact, the even higher temperature gave them so much hope. Oh, look, it's doing it. Oh, no, okay. This was such a big problem in science because it proved, well, it seemed to suggest that light was not a wave, even though other experiments clearly showed light was a wave. How can two things be true at the same time? It was such a big deal. They called it the ultraviolet catastrophe, because a lot of this stuff that you're seeing here was happening in the ultraviolet the ultraviolet part of the spectrum. You can see like this is where stuff got real and depression set in.